just a single point. And the task is to find the point in our data set that's closest to Q, right? Closest with respect to some sort of metric or similarity measure. Now, nearest neighbor search is a very deep problem in theory, and it's been studied for decades and decades in all sorts of contexts. And there's tons of algorithms for solving nearest neighbor search. Many of them are pretty complicated, but with simple ideas. But today I really want to focus on the simplest ways to solve nearest neighbor search. Right, so let's think about what is the simplest way to solve it. The simplest way is I'm going to brute force scan through my data set. I'll just look at all of my data points, and I'm going to find the one that's exactly closest to the query. Now, this algorithm always gives you the right answer, but it's not great because it takes linear time. We'll be interested in much, much faster algorithms for solving nearest neighbor search. Now, let's say I wanted to do something similar, but a bit more clever. Right? Maybe I still want to scan through my data set, but I want to scan through in a more structured way. The first thing I might do then is to build a structure on my data set, right? Maybe a graph on my data points. And then to scan through this graph, I might do a greedy search. Right, so what do I mean by greedy search? Let's say that these are my data points in the plane, for example. I'm going to start by building some sort of directed graph on my data points. And then when a query comes in, I'll choose some vertex S as my start vertex, and I'll do the following greedy process. At each step, I'm going to look at all of my out neighbors in the graph. And I'm going to jump to the one that moves me closest to the query. Right, so in this case, I just have one out neighbor. The next step, I have these two out neighbors, so I'm going to hop to the one that's closer to the query. And I'm going to keep repeating this process until I finally arrive at this point P, where I still have an out neighbor that takes me to the bottom right, but that would move me further away from the query. So I'm going to stop at P, and I'll report P as my candidate nearest neighbor. All right, so you might be thinking, like, okay, this is certainly one way you could solve nearest neighbor search, but why would we ever think of doing this? Like, where does this graph come from?
Doesn't it give you the wrong answer?
Yes, in this case, it gave you the wrong answer. You might ask, like, why should we expect this to give us good answers at all? And it turns out that, I mean, this idea of using a graph doesn't come from nowhere. If we kind of think about the real world, right? If you think about like real world networks, like social networks or the internet, they're large and complex and geographically separated, but nonetheless, they exhibit what's known as a small world behavior. So, for some context, like in the late 1960s, there's this very famous experiment by Milgram. And the experiment was to send packages from Nebraska to Boston through the hands of random strangers. And the only rule given to these strangers was to pass the package to a friend that you know lives closer to Boston. And what Milgram found is that in only in a chain of only length 6, in median, you're able to send a package halfway across the country. So this principle of 6 degrees of separation was really popularized by this experiment by Milgram. Now, near the turn of the century, Kleinberg sought to formalize Milgram's experiment in a computational model. Right, so Kleinberg modeled people as living on this vast two-dimensional grid. And each person, and they have their 4 grid neighbors, but they're also given a small number of random long-range connections. And Kleinberg was interested in when this rule of always moving to the neighbor closest to the target allows for efficient short paths from one end of the network to the other. And basically found that with the right distribution of these random long-range edges, such short paths are possible. Now, when we think about nearest neighbor search, our data set is not going to look as clean and nice as a two-dimensional grid. It might be arbitrary, high-dimensional data that we don't really know how to structure. But nonetheless, our question is going to be the same. Can we make arbitrary data navigable? And can we take advantage of this navigability to solve nearest neighbor search? And what's cool is that this question is actually the motivation behind a lot of modern nearest neighbor search heuristics that are used in practice. All right, I'll touch a bit more on this in a bit. So let me unpack what I mean by saying make arbitrary data navigable. What does it mean to be navigable on a data set? Well, let's say I have a data set with some distance measure, and also a directed graph where the vertices of my graph correspond to data points. I'm going to say my graph is navigable if for any source and any target, there's always an edge from my source that moves me closer to the target. Right. So one way you might interpret navigability is this condition that if I run my greedy search algorithm with a particular target in mind, I will eventually converge to my target. You stare at this definition, you'll see that these two things are equivalent. Now, just to make sure we have an example of a navigable graph in mind, let's picture again the grid graph in 2 dimensions. Now, this is a navigable graph because for any point S and T, I can always find an edge that moves me closer to T. In fact, usually there are 2 edges that move me closer to T. And if I imagine in this example running a greedy search from S to T, well, I'll kind of take this zigzag path, but I'll eventually converge to T, right? Because my graph is navigable. All right, so navigability is this clean and local condition that ensures that our greedy search algorithm will always converge. Well, let's think a bit about what it means for nearest neighbor search. And it actually turns out that navigability alone doesn't imply anything interesting for nearest neighbor search. So to sort of see what I mean by this, let me first say that in theory, it's common to study nearest neighbor search through the lens of approximation, right? So returning the exact nearest neighbor is an intractable problem, so it's common to study the approximate nearest neighbor search problem. And here, the task is to return any C approximate nearest neighbor of the query, any point whose distance to the query is at most C times the true nearest neighbor distance. Now, it turns out that navigability can't even solve this easier approximation problem with any interesting guarantee. And to see why, I want you to picture an example of 3 points on the plane. Right? So these 3 points, they almost form an equilateral triangle, but this length between S and T is 1 plus epsilon. Now, this graph that I've drawn, this sort of wedge graph, where I've omitted the edge from S to T, this is a navigable graph. Because if I wanted to navigate from S to T, I could take this edge to T prime. And that decreases my distance from 1 plus epsilon down to 1. So this is a navigable graph, but let's see what it means for nearest neighbor search. And it turns out that if I think of planting a query very close to T, let's say epsilon close to T, and then I think of running a greedy search from source S, I'm not going to move anywhere. And the reason I'm not going to move anywhere is because if I took the edge to T prime, that would move me further away from my query point. And so my greedy search will return the point S, and this is a problem because my distance to the query is now 1, whereas the true nearest neighbor distance is epsilon. And epsilon can be made arbitrarily small, which drives my approximation factor arbitrarily large. Yep.
Sorry, what's the distance between T prime and Q here?
It's more than 1. Like, I don't know what it is.
Sure. Okay.
You can imagine if Q is at T, they're equidistant. If you slide Q closer to S, you're going to get closer to S faster than you get closer to T. So, all right. This means navigability alone is not enough for any interesting guarantee on approximate nearest neighbors. But what I think is really interesting is that one small fix will change the game completely. So, again, navigability just meant that for any source and target, there's always an edge that moves me closer to the target. all I'm going to do is introduce a parameter alpha. And I'll say my graph is alpha navigable if, for any source and target, there's always an edge that moves me closer within a factor of alpha. All right, think of alpha as something that's more than 1. Now, I like to think of alpha navigability as a small world property. And the reason I like to think about it as a small world property is if you imagine running a greedy search on an alpha navigable graph, at every step of the search, your distance to the target will drop by a factor alpha, at least. And so the length of your greedy search will be a logarithmic number of steps. Now what's interesting about alpha navigability is that, surprisingly, it has an implication for approximate nearest neighbors. So there's this paper from a couple of years ago by Erik and Ashwin that shows that if you run greedy search on an alpha navigable graph, you are guaranteed to obtain an alpha plus 1 over alpha minus 1 approximate nearest neighbor in a logarithmic number of hops. So if you think of sliding alpha closer and closer to 1, this approximation factor blows up to infinity. That's basically the example we saw on the last slide. But for a reasonable choice of alpha, like alpha equals 2, this gives you a 3 approximate nearest neighbor, right? It's pretty good. And so what I want you to take away from this theorem is that if you gave me a sparse alpha navigable graph on my data set, I would immediately have a fast approximate nearest neighbor search algorithm. And the reason I want my graph to be sparse is because at every step of my greedy search, I'm going to scan through my entire out neighborhood. And so the runtime of my greedy search is roughly proportional to the degree of my graph. Okay. So that's maybe a good time to stop if there's any questions.
You're not allowed to add nodes.
No, not in how I'm fitting it here. But that is an interesting question. All right, so this is a nice result that kind of ties together this notion of navigability in approximate nearest neighbor search, but kind of leaves a very natural question as a follow-up, which is, like, do these sparse alpha navigable graphs actually exist? And even if they do exist, is there an efficient way to find them? So this is what the talk will be about: building alpha navigable graphs and building them efficiently. Now, I do want to say that, as I mentioned before, a lot of the heuristics that are used in practice, like disk-ANN or HNSW, if you've heard of these, they're kind of motivated by this idea of navigability, but they don't actually build alpha navigable graphs. They do something kind of different. But there are a couple things that we do know from theory. So the same paper by Erik and Ashwin, they analyzed kind of a theoretical version of this disk-ANN heuristic. And they showed that this algorithm always builds you an alpha navigable graph with bounded maximum degree. I'll get into what this bound means in the next slide, so don't worry too much about it right now. Right, so this particular algorithm always gives you an alpha navigable graph with some sparsity guarantee. And last year, there was this follow-up work, which really focused on the case of alpha equals 1. And they showed that for any metric, there's always a 1 navigable graph with not too many edges, okay, at most n to the 1.5 edges. And they proved the matching lower bound as well. Now, when I was sort of looking at these results with my advisors, I sort of realized that both of these results are really like global upper bounds. Like for this particular algorithm or this particular setting of alpha, you have some bound on the sparsity of the graph that you produce. And we were really interested in applying an approximation algorithms framework on this question of sparse navigability. So we kind of proposed this problem, the sparsest navigable graph, which is as follows. So let's say that you're given a particular data set as input, and you're also given alpha as input. Can you design an algorithm which builds the sparsest alpha navigable graph for that particular data set? And we're really interested in like this trade-off between how fast we can build the graph and how well we can approximate the sparsest navigable graph. And just as a note, like, we're going to assume that distances can be computed in constant time, or if you want to think about it differently, like the input of your algorithm is like an n by n distance matrix. And the way that we'll measure sparsity is we want to minimize the maximum degree of our graph. Although all of the results I'll talk about today also hold for minimizing the number of edges. All right. So, first way we kind of applied our framework was actually to give a negative result. So in the previous slide, I mentioned that there was this paper by Erik and Shu that showed that this particular algorithm called slow disk ANN, I'm not going to go into the details, it always gives you an alpha navigable graph whose maximum degree is roughly at most alpha to the power of the doubling dimension of your point set. Okay, doubling dimension is just some notion of dimensionality for general metric spaces. And if you look at this result, you might think, okay, like slow disk ANN might be a good algorithm. It always has this nice guarantee that scales with dimensionality. And what we showed is that from the lens of worst case approximation, slow disk ANN is actually quite a bad algorithm. All right, so we were able to find a data set where on this data set, there exists a sparse one navigable graph. All right, the degree of that graph is roughly O of log n. But if you run slow disk ANN on this data set, you're going to get a graph of degree theta n. And so from the perspective of approximation, slow disk ANN basically gives you the worst you could possibly hope for. It's omega tilde n approximation. And this is sort of interesting that like a heuristic that was studied in a previous work actually performs very badly through our framework of worst case approximation, which kind of motivated us to think of, like, are there better algorithms that have very strong guarantees in the worst case? So this is what I'm going to talk about in the next part. I'm going to show how this sparse navigable graph problem is really just a collection of set cover instances. And this allows us to design algorithms, approximation algorithms, with good worst case behavior. So to sort of see this connection between sparse navigable graphs and set cover, I want you to think about this alpha navigability condition, but from a single source vertex S. Okay, so from the vantage point of a single source vertex, alpha navigability means that for any target, there's an outgoing edge from S that moves us closer than factor alpha. And if you stare at this for a bit, you might notice that this is equivalent to an instance of set cover, where my elements of set cover correspond to all the targets that I want to cover, all right, everything other than S. And for every edge S to U, this corresponds to the set of targets that that edge would cover. Every target for which the edge moves me closer by a factor alpha. The size of your set cover then is in correspondence with the degree of your alpha navigable graph. So the degree of S in your alpha navigable graph. And so if I want to minimize the maximum degree, I just want to find a minimum set cover for this instance. Okay, so each source vertex corresponds to a set cover instance. So the entire alpha navigability condition is nothing but like the collection of these n set cover instances, one per source vertex. Just to get a picture in mind of how this set cover connection works, let's say I have a source vertex S on the left-hand side, and then on the right-hand side, I have all my targets that I want to cover. Now, maybe a natural thing to do here is pick these four vertices, U1 through U4. Right? Seems like every target is sort of close to one of them. And the way I can verify that I've satisfied all alpha navigability conditions is, well, for each of these edges, there's a set of constraints that drawing that edge would satisfy, and I've satisfied alpha navigability from S if the union of these sets covers all of the targets. Right? So, again, alpha navigability is nothing but these n set cover instances. So let's try to turn this observation into an algorithm. Now, each instance contains n-1 elements corresponding to the targets, and n-1 sets corresponding to the edges I could draw from S. So building my instances will take O of n squared time, and then running a greedy set cover algorithm will also take n squared time. And it will give me a log n approximation to the optimal set cover. Right, so just this immediately gives us an n cubed time algorithm for a log n approximation to the sparsest navigable graph. Right, so because each of the instances takes n squared time, and I have to do them over all source vertices. Right, so immediately we have this polynomial time algorithm for obtaining a log n approximation to the sparsest navigable graph. And it turns out that the connection to set cover actually runs in both directions. So our second mini result here is that it's actually NP hard to do any better than a log n approximation. And the main idea, which I'm not going to really go into in this talk, is we're going to encode set cover as a navigability condition by constructing the right metric. Right. So we have a polynomial time, an n cubed time algorithm for building a log n approximation of the sparsest navigable graph. But we shouldn't expect to do any better in terms of approximation in polynomial time. Sort of leaves out an unnatural question, which is, can we compute a similar approximation, maybe an O of log n approximation, in subcubic time? Right, so this will be what we'll talk about next. How can we design even faster algorithms for building navigable graphs that move beyond the naive set cover approach? Right. Any questions from this work?
If I only wanted an undirected graph, I didn't want out degree.
Yeah.
I just wanted to find edges and I'll check among all my undirected neighbors. Does the same work? Because then you're summing up the degrees over all the n circle.
Sorry, I'm not exactly.
So instead of building a directed graph,
Yeah.
I want to build an undirected graph.
And you want to approximate the best undirected.
No, and I, instead of looking out among my out neighbors, I just look among all my undirected neighbors. And
Yeah.
I want the alpha navigability condition.
Okay. I haven't thought about that, but it seems like it might be similar to.
Okay.
Yeah. Right. Okay, so let's start by thinking about what was the reason why we incurred n cubed time in the previous approach. And it turns out there's actually two reasons for this. But the first one is kind of more fundamental. So even if we want to just build our set cover instances, well, this involved building n squared many sets, like one per each edge that we could potentially draw. And building each set would take linear time. And so even writing out my set cover instance is going to cost me cubic time. And this sort of seems like a problem. Like, how can we even solve these set cover instances if we can't write them down? But there's one thing that helps us, one kind of property of our navigability problem that helps us, which is that if you gave me a particular target T and a particular set corresponding to an edge from STU, I can check whether the element is contained in the set in constant time, right? All I have to do is check whether the distance from U to T is smaller than the distance from S to T divided by alpha. So this is a constant time operation. And so this observation really motivated us to think about set cover in a different input model. Right? So rather than thinking of the input sets being explicitly written down as an input to your algorithm, we actually thought of a model in which you're given query access to the input. So in particular, you can only access the input by making queries of the form, is element X contained in set S? and we'd like to design fast algorithms for set cover in this particular model. Now, I will note like set cover has been studied in like query access model before, but surprisingly, it's never been studied in a pure membership model. It's been studied in more of an adjacency list model. This corresponds to an adjacency matrix model. So, question of, can we design fast algorithms for set cover in this membership model? Turns out the answer is yes. So, if I'm given an instance of n elements, n sets, and where the minimum cover size is k, our main lemma here is that we can build a log n approximation to the optimal set cover in this membership model in time that looks like mk plus nk. Okay. Now, let's sort of understand what this implies for our sparsest navigable graph problem. So, nk plus nk, well, n, if you remember, corresponds to n minus 1, and k corresponds to the best degree you could hope for on a given vertex. So, if you run these set cover algorithms at each of your source vertices, we'll obtain an n times opt size time algorithm for a log n approximation. And opt size here refers to the minimum number of edges in any alpha navigable graph. So if the best alpha navigable graph for your instance contained like n to the 1.5 edges, our runtime will be n to the 2.5. All right, let's actually make this like these consequences a little bit more concrete, right? Because yeah, so this n times opt size time algorithm for log n approximation. Let's see what it actually means. Right, if the minimum number of edges in your in an alpha navigable graph on your data set was like very close to n, like O tilde n, this immediately gives us quadratic runtime, right? A lot faster than the cubic upper bound that we saw before. And if you remember from a few slides ago, there was this previous result that showed that when alpha equals 1, there always exists the one navigable graph of n to the 1.5 edges. So this immediately gives us an n to the 2.5 time algorithm for the case of alpha equals 1. Right? Now, there's also cases when opt size can be quite large. I'm going to touch on that in a little bit. All right, so now I want to go into a little bit more detail with how we actually proved this fast set cover algorithm. And the idea will be fairly simple. It will be that we want to simulate the greedy set cover algorithm with random sampling. And if you remember the greedy set cover algorithm, all it does is it says, okay, if I always pick the heaviest set at every step, like the one that covers the most number of remaining elements, I'll cover a 1 over k fraction in every step, and so I'll be done in k log n many rounds. That gives me a log n approximation. Right. So let me just kind of do an illustration of how this is going to work. So we're going to start by sampling a small number of sets. Wait, sorry. In this diagram, we're just given a set cover instance with 5 sets and 12 elements. And I just want to give like the idea of how we're going to find a heavy set. We're going to start by sampling a small number of sets, let's say S2 and S4. And then we'll sample a small number of elements, let's say X6 through X8. And we're only going to make membership queries on the sampled sets against the sampled elements. So in this case, we'll just make 6 membership queries. And in this example, we'll notice that the set S4 hits 2 elements out of our sample. And so that kind of gives us some confidence that maybe S4 is a good set to add to our cover. So let me just formalize this intuition a little bit. The goal for a log n approximation, or an O of log n approximation, is to find at every step a set that covers omega 1 over k fraction of remaining elements. Now, I want you to imagine a universe where maybe like in the optimal set cover, it's relatively balanced. So you have k sets lying out there that each cover a 1 over k fraction of your universe. And the goal is simply to find one of these k heavy sets. And the way we'll do it is we'll start by sampling roughly m over k sets, which guarantees with high probability that one of the heavy sets makes it into our sample. But now we actually have to find which of these sets are heavy, right? Which of the sets that we've sampled is actually heavy, so we can return it. And the way we'll do this is just by a simple sampling check. We'll sample k log n uncovered elements, and that will give us the guarantee that if a set hits omega log n elements, it must be heavy with high probability. All right? So let's think about how many membership queries that we made. Well, we compared m over k sets with k log n elements, and so the number of queries we needed to find a single set was roughly O tilde n. And if we compare this with the number of queries we would need to find the exact heaviest set, well, that looks like m times n, because you have to read all of your sets to find the exact heaviest set. So this sampling trick sort of saves us a factor of n. And so putting it all together, like what's our final algorithm going to actually look like? We're going to keep calling this find heavy set procedure until we retain a full cover. And this will take k log n rounds. At each round, we take n queries to find a heavy set. And then there's one detail I left out, which is we need to actually maintain the set of uncovered elements so that we can sample from them during our find heavy set procedure. And the cost of this is n queries per round, because you just have to check every time I get a set, which elements did it cover. So in total, we get our log n approximate set cover in nk plus nk time. And just to restate what I said before, this implies we get an n times opt size time algorithm computing a log n approximation for the sparsest navigable graph. Now, if you sort of look at this result, previously I talked about a few cases when this gives us much better than n cubed time. But you can also ask, what if my opt size is very close to n squared? So maybe like, what if like my data set, the sparsest alpha navigable graph is actually quite dense? Well, then my runtime looks more and more like n cubed. And so in the second main algorithm, I'm going to show how we can actually get around this. Yeah.
Can opt size not be much smaller than nk?
Yes, it can. So
why does it imply? Why does the level imply result 3?
well, yeah, and sorry, nk can be much smaller than opt size. So basically, like from each source vertex, my time complexity would be n times the best possible degree of that particular source vertex. And yeah, all the sources are sort of disjoint conditions. So okay. So to sort of show how we can beat n cubed in all infinite instances, I'm going to define a kind of relaxation of our notion of approximation. Right? It will be a sort of bi-criteria approximation. Right. And the definition is a bit of a mouthful, so I'll just go through it a bit slowly. So, as before, the task is still to build an alpha navigable graph. But in this relaxed notion, we're also given a parameter beta. And the only difference from before will be how we measure, or basically the number of edges we're allowed to include in our alpha navigable graph. Right? So I'm going to let k sub beta denote the sparsity of, or the maximum degree of the sparsest beta navigable graph. And this could be potentially much larger than k sub alpha, because beta navigability is a stronger condition than alpha navigability. And the guarantee I'd want to satisfy is that the degree of my graph is not too much larger than k beta. So it's at most our approximation factor times k beta. Okay. So under this bi-criteria notion, we're actually able to do much better than n cubed. So here we're able to get a matrix multiplication time algorithm for computing a log n approximation to the sparsest alpha navigable graph if you compare it to the sparsest 2 alpha navigable graph. omega is the matrix multiplication exponent. All right, I'm not going to go too into detail with this algorithm, but I want to give like the main ideas behind like where matrix multiplication shows up. And to do this, I want to ask like a simple question that we haven't really touched on yet. Let's say you gave me a graph and you claim that it's alpha navigable. Is there a way for me to actually verify that it's alpha navigable efficiently? Right? Because like the naive thing I could do is, well, I'll look at your graph, I'll look at all sources and all targets, and I'll just check through all the edges and see if that target was satisfied. The problem with this is the runtime kind of grows with n squared times the degree of your graph. And so if you're dealing with a very dense graph, which is kind of what we want in this regime, this could take up to n cubed time. So let's think a little bit about how to do this in a more clever way. So it turns out that we can actually verify these navigability constraints in bulk. And the way we'll do that is, well, let's take a particular source and target whose distances are. We're going to draw two n by n matrices. One's called A and one's called B sub R. And A will be nothing but the adjacency matrix of our graph. B sub R will be nothing but the indicator matrix of all the small distances in our point set. Okay. Now, it turns out that the alpha navigability constraint from S to T is satisfied by our graph if and only if the matrix product between A and B sub R is non-zero at the entry ST. And this is sort of because if you imagine writing out the matrix product, one of the terms is non-zero if and only if there's an edge that corresponds to a short distance. It's exactly the same condition as alpha navigability. So from this observation, we'll immediately get this nice lemma, which is that if our point set had a small number of unique distances, let's say at most L distances, then we can verify all the alpha navigability constraints in time L times n to the omega, right? L many matrix multiplications. For each unique distance, we'll build this matrix B sub R, and then we'll compute all these matrix products. And then for a given constraint S and T, I'll just look at the product that corresponds to their distance. All right. So let me show how this verification lemma allows us to build a fast algorithm. And I'll really just sketch the algorithm. I'm not going to go into too much detail here. The first step is we're going to discretize all the distances in our point set, right? Say the powers of 1 plus epsilon. And this will ensure that our verification can be done relatively quickly. Now, after we've discretized our distances, we're just going to follow a simple procedure. We're going to sample some number of uncovered constraints, okay, like pairs ST where the alpha navigability constraint has not yet been satisfied, and we're going to add the edges that correspond to these constraints. And then we'll run our verification algorithm to find the remaining uncovered constraints after we've added these edges. And kind of a key property of this procedure that I'm not going to prove here is that each round will actually eliminate a constant fraction of all constraints, which means that will be done in a logarithmic number of rounds, and this gives us a result that will get this log n approximation in time O tilde n to the omega. Okay. And I do want to mention, I've been talking about like a data set with a metric this whole time. We actually haven't used the triangle inequality yet, but this result is the only result in our work that uses the triangle inequality. So I think it's kind of cool that it's unique to metric spaces. All right. Now, we kind of write down our two kind of faster algorithms. Both of them are dealing with log n approximation. Both of them take take better than n cubed time in some regimes, but both of them take super quadratic time. right? You basically have to read the entire input to run any of these algorithms. You could ask, can we design much, much faster algorithms, maybe even subquadratic algorithms, if we're willing to trade off our approximation factor? And in the last part of the talk, I'm going to show a lower bound that proves that we can't do this, actually. And it's quite strong. It says that if you want any non-trivial navigable graph, so in particular, if you want any little o of n approximation to the sparsest navigable graph, you better read your entire input. You can't do better than omega n squared queries to your distance function. And the idea will be fairly simple here. It's motivated by this observation that in a navigable graph, if you look at your closest pair in your data set, to the points that have the minimum distance, you have to have an edge between those 2 points. And the reason you have to have those 2 points is if S and T are the minimum distance, well, if I want to navigate from S to T, there's nowhere else for me to go. I have to go directly to T. Okay. So then the game here will be, I'm going to fix a metric that has a constant degree navigable graph, very, very sparse. And then I'm going to shrink a random distance in my point set to the minimum distance. And this will sort of create like a hidden shortcut in my metric that my algorithm will have to find. And in order to find it, I'm going to need to make n squared queries. Okay. So there's probably many ways to do this. The way that we did it in our paper is we'll fix like this sort of path metric where the distance from I to j, so I and j are both numbers from 1 to n. The distance from I to j will look like 1 plus I minus j over n minus 1. And to perturb this metric, I'm going to sample a random pair and shrink their distance down to 1. The reason I've sort of defined my metric like I did is so all of my distances are between 1 and 2. And so when I shrink my distance down to 1, I don't violate the triangle inequality. Right? Now, what does this metric look like? I don't know why it got dimmer, but hopefully you can still see it.
It's the projector.
It's a projector, okay.
Could you expose it?
I don't have too much left, so I wrap up. So the so if I look at my metric, there's a very sparse navigable graph that I can draw. Namely, if I take this path graph and add the edge from I star to j star, this gives me a degree 3 navigable graph. But because I'm forcing any navigable graph to contain this random edge I star j star, this means that if you want a graph of degree little o of n, you better query the entire distance matrix to find this pair. And if you look at this construction a bit more closely, you might realize that this is nothing but like a hard instance for closest pair. And so this other paper that I kind of talked about at the start extends this lower bound to Euclidean with like a closest pair reduction. All right. So this is telling me to wrap up quickly, so I can just get to the last slide here. So we sort of saw that there's like 2 algorithms and 1 kind of strong lower bound. So in n times op size, I can compute a log n approximation to the sparsest navigable graph. And also in matrix multiplication time, I can get the same result if I'm willing to accept this bi-criteria relaxation. But in n squared time, or rather, if I want any non-trivial approximation, I shouldn't expect to do any better than n squared time. Now, there's this concurrent paper that had some pretty strong results as well, and they were mostly focused on the case of alpha equals 1, and they actually showed you can get a matching lower bound of n squared time for a log n approximation. And even for alpha more than 1, it had some sort of balancing argument that shows that you can actually do n to the 2.5 time for a log n approximation as well. And so there's a few like interesting open questions here. I think the one that might be most interesting and like directly follows from these papers is, can we get a quadratic time algorithm for a log n approximation for the case of alpha more than 1? Either in the normal notion of approximation or this bi-criteria relaxation that I talked about. But yeah, that was everything I wanted to talk about today. Thanks so much for listening.